In a far corner of our solar system, orbiting quietly, lurks one of the biggest threats to the survival of the human species. Somewhere up there is an asteroid with our name on it.
The first indication that we have of the doomsday asteroid could be the first shock wave hitting the top of the atmosphere 5 seconds before impact.
Almost every individual human would die in an event of this kind. The question is not whether or not we will have a large impact in the future, but simply when.
This is the story of the struggle of science against oblivion. The race against time to find a way to save the Earth and all the people on it from asteroid Armageddon. The Canadian wilderness is vast and sparsely populated, fortunately. In the middle of January 2000, something happened here that shook the small town of Atlin from its winter hibernation.
It was early in the morning, I don't know, 8:30. I come out to start the pickup, and all of a sudden everything just lit up, multicolored, and there was a big roar.
This incredible white light just illuminated the inside of the truck. And as I stopped the vehicle and shut it off, it did it again. More intense than the first time.
So I look out in the sky and I see this fireball, and it just stopped.
At that point, I was like, now I don't know what's going on, and I quickly just ran out of the truck and I ran towards the house.
Then ashes and little pieces of fire were twinkling and were all running down, and it was right there.
Oh, you could feel it. Absolutely, you could feel it. My wife first thought that perhaps someone dropped a bomb.
I mean, this brilliant flash, but then these luminescent clouds, and you're like, we thought an aircraft had blown up. There was a lot of fear, I think, for a lot of people.
What they had just seen was a 200-ton asteroid exploding high in the Earth's atmosphere. An asteroid of that size hitting the Earth would have the destructive power of a nuclear bomb. But the people of Atlin had got lucky. It had disintegrated long before it hit the ground. But how much longer can the Earth's luck hold? In 2001, an asteroid exploded high above the Pacific Ocean with all the power of 10 Hiroshima bombs. In 2002, another blew up over the Mediterranean. How much longer will it be before an asteroid makes it through the Earth's atmosphere and hits an area of dense population? How long till Armageddon? Once upon a time, we thought we were safe. Death by asteroid, scientists thought, belonged to the realm of ancient history and Hollywood. True, everyone accepted the dinosaurs had been wiped out by such an event, but that was 65 million years ago. Such things didn't happen today. But just a few scientists dared to differ. Astronomer David Levy was one of them. He was no wild-eyed prophet of doom. What he had seen through his telescope convinced him that the world really did face a genuine threat.
The chances that we're going to eventually be hit by a large comet or asteroid is 100%. I can promise you that. And if you don't believe me, go out any night that the moon is up. Look at the moon. The moon is a record of the impacts in this region of space. The Earth erases most of hers because of weathering and erosion and mountain building and oceans. But not the moon. The moon is all there. Each one of those craters tells a story and tells a warning.
But on Earth, the few warning signs there were missed. Giant impact craters, great pockmarks on the Earth's surface, were dismissed as spent volcanoes. Only a few geologists and astronomers realized their true identity. And when they warned people that the type of asteroid that made them would one day strike again, no one would listen.
If you talk about the chance of life on Earth being partially annihilated because of the impact of a comet or an asteroid, and you try to tell that to the public, they giggle, they laugh at you.
But then something happened that would wipe the smile off the smirkers' faces. Something sobering.
January of 1993, the big problem was the giggle factor. July 1994, the giggle no more.
It all began at the Palomar Observatory in January 1993. David Levy, Carolyn and Gene Shoemaker were hunting for asteroids and comets when Carolyn aimed her telescope at a corner of the solar system near Jupiter.
Suddenly she peers into the telescope and she says, "I don't know what I've got, but it looks like a squashed comet." It looked like there were 5 or 6 comets all joined together, like linebackers running down a football field with tails behind them. It was really quite spectacular.
They named this weird, strung-out comet Shoemaker-Levy 9.
All we knew that night was that some catastrophic disruption had happened to this comet.
But it was the orbit of Shoemaker-Levy 9 that caused a sensation. It was on a collision course with one of Earth's nearest neighbors, Jupiter.
You find a comet that's split up into many pieces. It's not really news. But you find a comet that's split up into 20 pieces and they're all going to go colliding into Jupiter like a freight train wreck. That is news.
The world of astronomy was poised.
We're hoping that we're going to see a lot, but there's always been the chance that we'll see very little.
Telescopes and cameras at the ready, Shoemaker-Levy 9 did not let down its expectant public. In July 1994, it put on an incredible show as vast fragments slammed into Jupiter.
Yeah, that's it. Oh my God! That's it. Look at that!
This is actual footage of the impact.
The collision was the first time in civilization that we had actually witnessed an impact in our solar system.
This one blast cloud is itself as big as the Earth.
Seeing a planet in distress, this is something that's been totally new. It's nothing like this had ever happened in the 400 years since the telescope was first looked at the stars by Galileo.
This impact on Jupiter was the most destructive event ever witnessed in our solar system. Overnight, the Earth had become a more vulnerable place. Our near neighbor in the solar system had been attacked in full view of the world. And if an impact could happen there, it could also happen here. Suddenly, asteroids became a matter of top government priority. The hunt was now on for potential extraterrestrial killers. All eyes turned to the asteroid belt, that strip of orbiting rocks that lurks between Mars and Jupiter. Here, great blocks of rock and metal, left over from the building of our solar system, quietly circulate. Most are harmless and will never come near the Earth. But just occasionally, they collide, sending one spinning out of orbit at 20 kilometers per second, several times the speed of a bullet. At that speed, a 1 kilometer wide asteroid could hit Earth with 20 times the power of all the world's nuclear weapons. The big question was, were any of these killer asteroids heading our way? After almost 10 years of searching and several false alarms, astronomers found what they most dreaded: a kilometer-wide asteroid with our name on it. It's known as 1950 DA.
An interesting question is 1950 DA the most dangerous rock in space? And at the moment, one could say it's the most dangerous known rock in space.
Astronomers have tracked 1950 DA more closely than almost any other asteroid in the solar system. And all the indications are it is cosmic enemy number 1. Expected to collide with or come perilously close to the Earth in 2880. Its impact could kill hundreds of millions of people.
If 1950 DA hit the Earth, it would release an enormous amount of energy. The object is about a kilometer, maybe a little bit more than a kilometer across. The energy released would be roughly 100,000 megatons. 10 megatons is a very powerful hydrogen bomb. So this would not be a pleasant event for the Earth.
It seems that in a mere 877 years, less than the blink of a cosmic eye, we have a date with Armageddon. And we may not even have that long. Asteroid hunters estimate that there could be up to 600 kilometer-sized asteroids still undiscovered near Earth. And any one of these could be heading straight for us. The world of science now faced an awesome task. What could it do to save the Earth? Ten years ago, Jay Meloche was part of an elite group of scientists summoned by the US government to tackle this new threat to humanity. Among the team was some of the American military's top weapons designers. The solution, they confidently proposed, would be to turn our weapons of mass destruction into weapons of mass salvation. Attack an incoming asteroid with nuclear missiles.
It would seem that a big nuclear weapon detonated either on the surface or drilled inside an asteroid would be the answer to this problem. I mean, we've been trained from watching movies like Star Wars that if we were to do that, the asteroid would disappear in a cloud of vapor.
But then, Meloche and his fellow scientists pointed to one very obvious snag.
Those movies ignore the really gigantic scale of these objects. Even a nuclear weapon of the normal yield, 20 megatons, would not disperse it.
Firing even our most powerful missiles, 20 megaton warheads, would be useless. In fact, it could just make matters worse. Scientists calculated that the explosion could simply shatter the asteroid, causing huge pieces of rock to rain down across continents and oceans. One huge killer would be turned into something every bit as deadly, a cluster bomb.
Even if we could break it up into fragments, it's not clear that that would help things unless all of the fragments missed the Earth.
Because if they didn't, gigantic fires could be ignited by those fragments hitting land. Large fragments that hit the sea could raise tidal waves up to 4 kilometers high. It seemed no existing nuclear weapon could save the Earth. What was needed was something much bigger. Something that wouldn't just fragment an incoming asteroid, but completely vaporize it.
Nothing that we have in our arsenals can release that much energy. Nevertheless, the nuclear weapons designers assure us that there is no theoretical limit to how big you can build a nuclear weapon, and many were eager to try.
So they set to calculating just how big a weapon they would need. The answer was staggering. The biggest bomb ever made would have to be placed on the biggest rocket ever made. And the whole contraption fired out of the Earth's atmosphere at 40,000 kilometers per hour.
We're talking something on the order of 1,000 megatons. Such weapons constitute a bigger threat to us than the asteroids themselves do.
This weapon, if mishandled or misused, would itself be capable of causing a global catastrophe. The idea was dismissed as insane. Nuclear weapons, it seemed, were not the answer. Science had to find a better way. That's when Al Harris and Tom Ahrens became involved.
So if we need to deflect an asteroid, if it's going to collide with the Earth, we need to change the course. Now, you could imagine applying a push in the...
Harris is an expert in the orbit of planets.
The new course oscillates...
Ahrens, a specialist in impacts.
...to a very large distance. The same happens...
They came up with an entirely new approach.
You then get an orbit that will go further out...
Don't blow up the asteroid.
...like this.
Just nudge it from its collision course with Earth.
So again, it oscillates. When we calculate that there might be an impact in the future, it amounts to saying that the Earth in its orbit moving along here and the asteroid like that will both be at the same place at the same time.
One way of looking at this problem is this. Imagine that the Earth is a train on its railway line, it's whizzing along, we can't stop it. We can't stop the train, we certainly can't stop the Earth. So it's like the Earth is barreling along on this railway line and there's a level crossing ahead, then we realize there's a car approaching. This is the asteroid. This asteroid is approaching. According to our sums, we find, hey, it's either going to be on the railway line at the time the train gets there, or it's going to be perilously close. We need to make sure it's going to miss. How can we do that?
What is necessary then is to change the orbit of the asteroid just a little bit so that, in fact, they're not at the same place at the same time.
The solution they came up with was again to use nuclear weapons. A 20-megaton missile might not be big enough to destroy a 1-kilometer asteroid. But if it was detonated just next to one, what they call a standoff blast, it could make it miss the Earth.
And we came up with the idea that if we set off an explosion close to the asteroid, but not quite on it, and maximized the radiation from the explosion, this would deflect it a few centimeters per second in velocity.
But would a change in speed of a few centimeters per second be enough to save the world? As they worked it out, they realized it was possible. First, they worked out how far they had to move the asteroid. The minimum safe distance they came up with was as far as the Earth is wide, 6,000 kilometers.
The Earth's dimension is 6,000 kilometers. 6,000 kilometers converted to centimeters is this many zeros.
Then they calculated how much the asteroid would have to be speeded up, given a realistic advance warning.
If you had, for example, 10 years, that turns out to be about 300 million seconds. And if you just do this division, you can get rid of all of these zeros. We have 2 centimeters per second.
The world could be saved by adding just 2 centimeters per second to an asteroid's speed 10 years in advance of impact.
That is a very slow speed. It's like the speed of this chalk moving across my face like that. That's all the faster we have to push in order for the asteroid to miss the Earth at the end of a decade.
It seemed a standoff blast 10 years in advance would push the asteroid safely past the Earth. With 1950 DA 800 years away, there would be ample time to save the world. Science had found the answer. Except, unfortunately, it hadn't. Ever since the meteorite had exploded over Tagish Lake in Canada, local inhabitants had combed the area, looking for any fragments that might have hit the ground. But no one found a thing. After a fruitless week, Jim Brooke was heading home across the frozen lake.
There'd been nobody in that area on the ice before, so certain I was probably the first one there.
Then he noticed some unusual dark shapes on the ice.
Well, there was stuff farther up the lake to the north and other things on the ice. I stopped and looked at a couple of these things because they were black. From a distance they looked like rocks, but it turned out to be animal droppings. And I thought that's what it was again until I got fairly close and I could see it was solitary and too big. And when I realized it was a rock, and it was very obviously a meteorite because it's half a mile out in the lake from shore.
Jim Brooke had discovered the only physical evidence of the asteroid. So he raced home.
No, Mother was the only person here. And when I came in, I told her I'd found something. So she got a little excited, and I got some of the pieces out of the bag and showed it to her.
And there was something puzzling about these fragments.
The first piece I picked up was probably in the order of 100 grams. And I was genuinely surprised at how little it weighed for its size. It was like picking up a charcoal briquette or a piece of pumice stone. I was fully expecting it to be quite a bit heavier, and very surprised at how light it was.
Word about Brooke's find spread quickly through the scientific community, and samples were sent off for analysis. Some of them ended up in London's Natural History Museum, where they have one of the biggest collections of asteroid fragments in the world. All were made out of heavy lumps of rock or metal. But not this one.
Oh, this is really unusual. This is not like anything I've seen before.
The Tagish Lake meteorite was subjected to a barrage of high-tech tests. And gradually, it became clear why the fragments were so light.
One series of measurements that was made on Tagish Lake very quickly was to measure its density and its porosity. It's got a very high porosity, very low density, which means that the object it's come from is, it's got a lot of airspace in it.
The Tagish Lake meteorite was full of air. It was the lightest meteorite ever found. This strange piece of information presented scientists with a puzzle. The standoff blast theory assumed that an asteroid was made out of dense rock or metal. All the calculations about how much it could be deflected were based on that one assumption. No one knew what would happen if the asteroid was made out of something weaker or lighter. Impact specialist Dan Dudder decided to find out. At this NASA laboratory, he blasts real meteorite samples with BBs, or pellets, fired from a huge air gun. His impact experiments in a vacuum tank mimic the effects of a nuclear blast in space.
We've been doing experiments on real meteoritic materials, material that real asteroids are made out of, because there was a sort of a lack of information in the scientific community on the response of real meteoritic materials to impact.
First, Dud observed how strong and solid meteorites were disrupted on impact, just as predicted. Then he experimented on weak porous samples, like those from Tagish Lake. And the results were very different.
You may send a BB slamming into a porous rock at almost 5 kilometers a second, and almost nothing will happen. The porous material will completely absorb the blow of the impact.
Whereas solid meteorites would be blasted out of the way, porous meteorite rock acts like a sponge and absorbs the force. The meteorite, representing the Earth-bound asteroid, hardly moves at all. The implications for the Earth are immense. A 1 kilometer wide asteroid as porous as Tagish Lake would still be enormously dangerous to life on Earth. But it would simply absorb the force of a standoff blast and just keep on coming. The question now was this just a freak one-off, or were there many others up there like it? The trouble is, it's impossible to know for sure what an asteroid is made of without actually sampling it. But as a rough guide, scientists began to look at how fast any asteroid was spinning. The basic rule is, the faster the spin, the more solid the asteroid. A slow spin means the asteroid is probably porous or made of loosely compacted pieces of rubble.
Our ideas of asteroids as solid chunks of rock in space have begun to evolve and change. Observations of the rotation rates of small asteroids. Some are rotating very rapidly, showing that they must in fact be solid chunks of rock. However, many other asteroids have a speed limit to their spin. And it tells us that they must be composed of loose piles of rock barely held together by their own gravity.
Using the speed of spin as a guideline, there was good news and there was bad news. 1950 DA, the Doomsday asteroid, spins surprisingly quickly, meaning it is probably made of something solid. It should be diverted by the standoff blast. The bad news was there are hundreds of slowly spinning asteroids out there, so potentially hundreds of asteroids would be immune to the standoff blast. For the Earth to be truly safe, science would have to find another, surer way of deflecting an asteroid.
5, 4, 3.
What was needed was more information.
We have the ignition. We have liftoff of the Delta rocket carrying the nearest spacecraft bound for the asteroid Heroes.
First, NASA had to figure out well in advance what type of asteroid might be heading our way, and so how best to deal with it. All eyes turned to a small probe, the near Shoemaker craft that was coming to the end of its long 3-year journey through space. One of its main mission aims was to find out all about the composition of Eros, a 30-kilometer wide asteroid. The obstacles the probe faced were formidable. Eros is far smaller than any planet or moon, and it is moving at twice the speed of a bullet.
Eros is a 30-kilometer object. It was more than 300 million kilometers away from Earth when we went there, and that's more or less like trying to land on the end of a human hair at a distance of 100 meters.
The official mission aim was simply to orbit and gather valuable scientific data. But secretly, the team had a much more ambitious plan.
We had the plan to land even before launch, but just mentioning it to various people on the project, well, the project manager, for instance, he wasn't too happy. And I kept hearing that I should not be saying the L word too often, especially if the NASA headquarters people are around.
No craft had ever tried to land on an object so small or so fast-moving.
Carrier's still locked.
Landing would depend on a complex series of delicate thrusts.
We haven't lost the signal yet.
One mistake, and the craft could have crashed.
Just a few hundred meters to go, and we're on track for a nominal land.
That's right.
But instead, as these descent photographs show, it landed safely.
Are we on the surface?
We're just unbelievable. Absolutely unbelievable. We're probably seeing detail now at the scale of a few inches.
I'm happy to report that the Near spacecraft has touched down on the surface of Eros. We are still getting some signals, so evidently it's still transmitting from the surface itself.
The success of the probe may prove to be more useful than anyone at the time predicted. It not only sent back valuable information about the composition of Eros, but by being able to get up so close to its target, it may have made a major breakthrough in how we could deal with these threats in future.
This is the first time that any spacecraft has landed on a small body.
Suddenly, a whole new kind of technology could be deployed. That technology had been dreamed up by J. Meloche, a long-time opponent of the nuclear option. He felt that what was needed was something that would gently and continuously push an asteroid off course, rather than a blast that could be absorbed. Early on, he realized that there was a huge supply of energy out in the solar system that could be used for just such a purpose. The sun. So Meloche put forward an extraordinary idea. He suggested building a device that would act like a giant magnifying glass.
We imagine this is the asteroid, we get it lined up, focus it, and we can start to vaporize the surface of the asteroid.
His name for this device was a solar collector. This solar collector would focus an intense beam of the sun's energy onto the asteroid. The heat would burn away the surface of the asteroid, releasing energy which would gradually push the asteroid off course.
If we focus the solar energy in a narrow spot on the surface, we can actually vaporize rock, generate a jet, kind of like a little rocket motor, a solar-powered rocket motor, that will then gently push the asteroid away. If we can keep this spot hot for long enough, it will eventually push the asteroid slowly and gently out of a collision course with the Earth.
His calculations showed that for his solar collector to work, it would have to stay close to the asteroid for many years. After the near Shoemaker probe to Eros, the idea did seem possible. But when he had presented the plan at an asteroid-busting conference dominated by weapons designers, the reception had been hostile.
I first proposed this as a serious method of deflecting asteroids at a conference where there were a large number of nuclear weapons designers present, and they reacted very negatively. I was accused of being a tree hugger. I was reminded that the sun shines by thermonuclear energy, and so one should love thermonuclear energy. It was not only not taken seriously, several people worked very hard to find objections to it.
Objections centered on the one obvious flaw in the plan. No one knew if you could even build a solar collector. The whole idea was branded as outlandish and dismissed. But a few days after the conference, Milosz received a cryptic phone call. It said that Milosz's collectors not only existed, they were currently being used.
Shortly after making this proposal, which I thought the technology was far in the future, I was astonished to find out that there is a company that's already making small versions of these parabolic mirrors.
But what was being collected was not sunlight. Instead, radio waves were being gathered by US intelligence on Earth. Milosz realized the same technology could easily be adapted to collect solar waves. The technology that Milosz needed for his asteroid-busting plan was already orbiting above him. Milosz's idea means that there may now be a new way of deflecting incoming asteroids, no matter what they are made of.
With this kind of concept and enough time, we could easily save the world from threatening asteroids.
The Milosz plan would begin with the launch of a probe equipped with the same technology as used on Eros. As long as there was some 10 years warning, the probe would have ample time to reach its target. Once up close, a huge solar collector could then be released. Slowly and surely, it would burn the surface of the asteroid, pushing it little by little off course. There would be no need for nuclear weapons, and the Earth really would be saved. We may not be so safe after all. In 1997, Comet Hale-Bopp appeared in our skies and passed just 190 million kilometers from the Earth. It's a long-period comet, a visitor from deep outer space. Such comets are rare, but what is disturbing about them is that they do not show themselves until they pass the sun, when their tails suddenly light up. Though such an event is highly unlikely, if one were to be heading towards the Earth, we would have at most just a couple of years. No nuclear weapons or solar collector could save us.
The problem with long-period comets is it sweeps into the inner part of the solar system, rounds the sun, and goes sailing out to nowhere. And for most of its time, it's just moving at a pace so slow that you could crawl and keep up with it. It's hardly moving at all. And then it starts moving back towards the sun, and it picks up speed, and it goes faster and faster and faster and faster. And if you get a long period comet, by the time it's about to hit the Earth, it's moving somewhere in the order of 60 to 70 kilometers per second. Something going that fast will cross the Atlantic Ocean between London and New York in about 3 minutes. You don't want something like that that's 10 miles across slamming into us. You just don't want to go there.
Next tonight on UK TV documentary, Dom Joly and David Aronovich join a pre-scandal Angus Deaton in Have I Got 2001 for you? Over on History, it's Karnak, A Hidden History. And on Gold, we're spending Friday night with Jonathan Ross.